this video, we're going to be looking at the solar system and the life cycle of stars, and this is video number 1 of 2 for our space physics topic. So let's get started. So, the solar system. Within our solar system, there is one star, which is the Sun, plus the 8 planets and the dwarf planets that orbit around the Sun. Natural satellites and the moons that orbit planets are also part of the solar system. So, this is the solar system. The solar system consists of the Sun, which is shown here on the left, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune and Pluto. Now, a very easy way to remember this, I find, is a little word sequence, and that's my very easy method just speeds up naming planets. So if you can remember those, it's the first letter of each of those words corresponds to each of these planets. So my very easy method just speeds up naming planets, or Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Now, our solar system is a small part of our galaxy, the Milky Way. So the Milky Way is shown there. Our solar system, those parts that I've just shown you, make up a very, very, very small part of our galaxy. A very small part. So there's hundreds and hundreds and thousands of stars which make up the Milky Way, and other planets and satellites and other things that you find in space as well. But our solar system is found within our galaxy, the Milky Way. And the universe is made up of many galaxies. So our galaxy, the Milky Way, is one of many, many millions of other galaxies which make up our universe. So the universe holds galaxies, and galaxies hold our solar system. So you have the universe, which holds galaxies, which holds lots of other systems like our solar system. So you need to know about the life cycle of stars. And we're going to start off by looking at the life cycle of stars which are a similar size to our Sun. So the Sun was formed like any other star. It started off with a cloud of gas called a nebula. The nebula has gravity. There are particles of gas clumped together, and this pulls in other gases to make the cloud even bigger. So even though a nebula is gas, it's gases, it still has a force of gravity associated with it. So it's still pulling in other gases and other bits of matter towards the cloud of gas, and this makes the cloud of gas grow. Now, when the nebula grows, more and more gas particles are drawn to it, and the force of gravity then increases even further. The particles are mainly hydrogen gas. So here we'll have a nebula, and we'll have the force of gravity pulling more things towards this nebula. It's pulling more hydrogen gas into this cloud. When the gravity of the nebula increases, the outside of it starts to move inwards. As this makes it denser in the middle, more and more matter starts collapsing inwards, and the temperature of the gas begins to rise. The gas's temperature begins to increase, and this is because the pressure of the gases inside the middle of this nebula is quite high, and when you have high gas pressures, it leads to higher temperatures. Now, when the temperature has risen and the pressure inside the nebula begins to rise, you are at the next stage of the star's life cycle. It is now a protostar. Now the temperature is much higher, and the pressure is now much greater as well. These conditions are perfect for nuclear fusion. Now, we covered nuclear fusion in the atomic structure topic, but in brief terms, it is the combination of nuclei to create new elements. Hydrogen fuses together to form helium. This releases energy and produces lots of heat and radiation. Now we are at our next stage. It is a main sequence star. At the main sequence, you get nuclear fusion in the centre of the star. This produces an outward force. The force is strong enough to withstand gravity pushing inwards. You get something called equilibrium. The amount of force pushing outward from nuclear fusion is equal to the force pushing inwards due to gravity. The star stays in this stage for a very, very, very long period of time. So it burns through hydrogen, fusing it into helium for a very long time. Once some of the hydrogen starts to run out and there is no more to fuse together and make helium, the star begins to shrink because the force of fusion is now below the force of gravity. So once the amount of fusion in the centre of the star reduces, there's not that force pushing out against gravity anymore, and the star starts to shrink and push in on itself. When this happens, pressure increases and the star starts to fuse together helium and creates heavier elements. The star then expands to form a red giant. So the force from fusion disappears, which makes gravity the dominant force, makes it shrink, and then it grows to become a red giant. The red giant is now fusing helium together to make heavier elements. So it's not fusing hydrogen together anymore, it's now fusing helium together. All elements up until iron on the periodic table are made during the fusion of nuclei here. Once the red giant runs out of helium to fuse together, it shrinks down to a much smaller star, a white dwarf. Once the white dwarf runs out of energy and stops emitting heat, it becomes a black dwarf. The star is no longer fusing nuclei and releasing energy. Once the star has become a black dwarf, the cycle is finished. All of this up to now applies to stars which are like our Sun, or a similar size to our Sun. So now we're going to have a look at what happens if a star is much bigger than our Sun. So the life cycle of a star which is much bigger than the Sun starts more or less in the same way, except everything's on a bit of a larger scale. So stars much bigger than the Sun go through a similar life cycle in the beginning. They start off as a cloud of gas or a nebula and turn into a protostar and then a main sequence star, as shown here. However, when a star much bigger than the Sun starts to run out of hydrogen and fuse together, starts to run out of hydrogen and fuse together and shrinks, the result is a swelling into something much bigger than a red giant, a red supergiant. Now, red supergiants fuse helium nuclei together just like their smaller partners, red giants, but they're just much bigger. So, once the force of fusion runs out, we get a red supergiant. Red supergiants combine nuclei to form heavier elements. All elements up until iron are made when this fusion has taken place. So just like its smaller counterpart, a red giant, red supergiants do fuse helium together, and then they'll fuse other elements together which are heavier than helium, all the way up until iron on the periodic table. Once the red supergiant runs out of helium to fuse together, it collapses. The red supergiant collapses to form a supernova. Supernova are incredibly hot, hot enough for the fusion of nuclei of elements to create elements heavier than iron. This is where elements which are heavier than iron and therefore much rarer come from, supernova. So if you look at the periodic table, elements which are heavier than iron can only come from supernova because they're hot enough, they have energy which is great enough to create all of these much heavier elements. What happens next depends on the size of the star. After a supernova, the star can become one of two things. A slightly smaller star creates a neutron star. A neutron star is a ball of very dense neutrons. Now, if the star is bigger, it creates a black hole. Black holes are so dense that not even light can escape. So where do the elements come from? Well, elements up to iron are made in stars similar to the size of our Sun. They are made in the red giant stage. Elements after iron are made in supernova. Now that means they're only made when a star is incredibly big. They are rarer than elements lighter than iron and are distributed throughout the universe due to the nature of the explosion of supernova. So supernovae are so powerful that they eject their matter miles and miles and miles, and that's how elements which are much heavier than iron are distributed throughout the universe. So let's just have another look at the sequence of the life cycle of a star. So all stars start the same as a cloud of gas and dust, or a nebula. That nebula then becomes a protostar. The protostar becomes a main sequence star, and if you are looking at a star which is about the same size as our sun, that main sequence star then becomes a red giant. After a red giant, it becomes a white dwarf, and then finally a black dwarf. If you're looking at a star which is much bigger than the sun, it starts off the same, but after the main sequence, it becomes a red supergiant, which is much bigger than a red giant. The red supergiant then goes supernova, and depending on the size of the star, it'll become a neutron star or a black hole. If you're following along in your revision workbook, pause the video now and complete task number 1.
Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backroadtutoring.com.